Hey everyone, Mr. Ferentz here. Today we're going to start talking about the first unit of AP Physics 2, which is fluid mechanics. Now, liquids are fluids, duh, but gases are also fluids. Anything that flows follows these rules and relationships that we're going to be studying. So, in the examples we'll be talking about today, in these situations, we'll generally be thinking about water because it's easy to visualize a tank of water or a pool of water and something floating in that water. But just keep in mind that all liquids and gases follow these rules and relationships. So what we're going to talk about today is called hydrostatics, which is about fluid that is just sitting in place. Okay, so this is not a river. This is not something in motion. This is just a tank of water or a fluid, whatever that fluid may be, just sitting in place, and then maybe something submerged in it or floating in it. Okay, so the first property of a fluid or an object that we're going to be looking at is density. If you remember back to chemistry, density is defined as mass divided by volume. And the variable we use for that is this Greek letter rho. It is not P, it is rho. Be careful. I will generally write it sort of like this with a little curly tail on it, sort of like a backwards 9 or a weird looking E. But that's how you write it. The unit in science class that we measure density in is kilograms per cubic meter. The way to just remember that is it's the unit of mass divided by the unit of volume. Sometimes you'll have the density given in grams per cubic centimeter. You just need to convert, and we'll practice that once we look at some examples. Another phrase that you will hear related to density is specific gravity, and that's just a ratio of the density of an object to the density of water. So if an object's specific gravity is 1, its density is exactly the same as water. If it's less than 1, it's less dense. If it's greater than 1, right, you get the idea. Another really important property that we have to pay attention to is pressure. This is defined, this equation here is the definition of pressure. It is force divided by area. So this is force measured in newtons, area which is measured in square meters. There are many, many different units of measurement for pressure, but the one we're going to be using in this class is the Pascal, which is, of course, named after an old dead guy. 1 Pascal is defined as if you imagine 1 Newton of force pushing down on 1 square meter. That's pretty small. So the pressures that we deal with in everyday life are going to be on the scale of tens of thousands or hundreds of thousands of pascals. So we're going to be using lots of scientific notation. And there's this relationship between pressure and force and area that you need to keep in mind. If we're poking someone with a finger or a needle, the amount of force we use can be the same. But depending on the area that we're applying that force to, the pressure can be very, very different. If we're applying it over a larger area, like our finger, it'll be kind of a small pressure. If we're applying it over a very small area like the tip of a needle, that pressure is going to be very great and will break the skin. So just keep in mind that sort of inverse relationship between area and pressure. And also keep in mind that pressure acts in all directions. So as this dude is swimming in water, the water is not just applying pressure pushing down on him. There's also pressure underneath that is pushing up. There's pressure pushing in from the sides. Pressure is always going to be acting perpendicular to the surface. And that's true for you right now with the air around you. It is acting in every direction perpendicular to the surface of your body and the clothes on your body. Now, as we go deeper into a fluid, the pressure will change as you dive to the bottom of a swimming pool. You will experience that the pressure gets greater and greater and greater. So this is the equation that tells us how to calculate that. This is a one we're going to be using a lot. So highlight it, put stars next to it in your notes. Be prepared to just have this easy to refer to. We're going to be using it a lot. Now this is rho, which is the density of the fluid, G, our old friend, 9.8 meters per second squared, and H. Now this is the depth in meters. Now we've used this as height, so we talk about the height, in meters above the surface. Here we're actually using this for the depth below the surface, which is just a little bit different. So if you're at the surface, your depth is 0, so the value of H is going to be 0. But as you go deeper and deeper and deeper, your depth increases, that value of H is going to increase. It is measured in meters. And so the pressure will also increase along with H. Just keep that in mind. At sea level, there's the air pressure pushing, it's literally the weight of the atmosphere pushing down on us. And this is a constant, okay? So this is a number we're going to be using over and over and over again. The atmospheric pressure, due to the weight of the atmosphere, is 101.3 kilopascals. So that's 101,300 pascals pushing in every direction on you. We talked about different units of measurement for pressure. So we can measure this in pascals or kilopascals. We can also measure this in units called atmospheres. So this value is also called 1 atmosphere. And there are some other conversion factors down here between different units of measurement for pressure. We have atmospheres, this is millimeters of mercury. This is used in barometers, in blood pressure cuffs. We have millibar, which is used in weather forecasting, meteorology. Later, we're going to look at some hurricane data, and they're going to be measuring their pressure in millibars. Generally, in this class, we're going to use pascals to measure pressure. You will never have to memorize these conversion factors, but you may have to convert back and forth to using that. So anyway, that's just for your reference. That atmospheric pressure is a constant. And when you actually use a pressure gauge, right, on like the tires of your car or something, the reading that it gives you, the thing it actually measures, is not the total pressure. It's just the pressure above and beyond the atmospheric pressure. This is called the gauge pressure. So just keep that in mind. If we see that, if you see that phrase in a question, just keep in mind it's not the total pressure. That total pressure is called absolute pressure. It's the sum of the atmospheric pressure, which is that constant 101.3, and the gauge pressure. So here it is in convenient equation form. And again, just remember that atmospheric pressure is always, always, always going to be this value. So that will wrap it up. For this, we're going to have another video on buoyancy and the buoyant force and Archimedes principle. So catch that. In the meantime, take care of yourself.